Okay, let's look at this review paper that was published a few years ago in Reviews of Geophysics, and it's a paper that tries to assess, once again, what Earth's equilibrium climate sensitivity is. And it looks at multiple lines of evidence, and some of this evidence is climatic. Here is the abstract for this. You could read this on your own when you download the PDF for the slides. So this is an extensive review trying to estimate Earth's equilibrium climate sensitivity, and this is the temperature change that would occur by doubling carbon dioxide content from 280 to 560 parts per million. The reason why we get a range of temperatures is because we're not exactly sure how the negative and positive feedback processes will work as the climate warms. Will there be more positive feedback leading to greater warming, or more negative feedback leading to less warming? So this paper evaluates the current understanding of how the feedback processes work, the historical climate record, and a much longer paleoclimate record. The paleoclimate record suggests that doubling CO2 creates an equilibrium climate sensitivity that is less than 4.5 degrees Celsius. They believe, based on everything that they've reviewed, that the 66% likely range is between 2.6 to 3.9 degrees Celsius for doubling carbon dioxide content in the atmosphere. The previous assessment report by the IPCC had a range of 1.5 to 4.5 degrees Celsius, a broader range. In the latest assessment, the models were more carefully tuned, and guess what? The models produced the same range as this paper suggests from historical climate evidence and paleoclimate evidence, much older paleoclimate evidence. The research concludes that the climate sensitivity is likely not less than 2 degrees Celsius, or would be or a value that is low enough to avoid substantial climate change. So based on the various scenarios, they provide their estimates of how much warming would occur under the various emission scenarios, with RCP 2.6 being the best case. RCP 4.5 is the probable case of what's going to occur in the future, because I do believe that there will be emission cuts. RCP 6 is a little worse case, and the business as usual case, if we do nothing, is RCP 8.5. So on the bottom scale, we have warming between 1995 and 2089. So it's a 30-year average, and then above is warming at 2089 relative to pre-industrial. So they're suggesting that RCP 4.5 probably the best case scenario of what's going to occur, because we really don't have our act together, is a warming in the range of about 2.5 degrees. The worst case scenario could produce a warming of the Earth in the range, the average value of about 4 degrees. But notice that this is a normal curve, and it is hoped that the models are correct, and that the middle value will be the value that occurs. So best case scenario, 2.5. Worst case scenario, about 4 degrees warming by the end of this century. And so this is the best case scenario. You can see that with that, we would be able to achieve that 1.5 degree Celsius threshold that scientists suggest that we shouldn't pass. Okay, the next paper once again looks at this idea of climate sensitivity, and it examines data from the last glacial maximum, and sort of works backwards to try to figure out what would be the equilibrium climate sensitivity if we doubled CO2. So it's using the past to predict the future, a common thing in earth science. Here's the abstract for the paper. So you can take a look at this. It's in the PDF slide set. So as you said, this research examines the last glacial maximum to see how climate systems respond to changes in greenhouse gases. Now, of course, we're going backwards, right? Not forwards. Uses a large collection of geochemical proxies for sea surface temperatures, so it's using sea surface temperatures. And it suggests that the last glacial maximum had a cooling relative to today of about minus 6.1 degrees Celsius, and a 95% confidence interval in between minus 6.5 to minus 5.7. So here is the distribution of samples that were used for this research. So you can see that quite a few samples. And then from that, they derived sea surface temperatures and surface air temperatures, so which are shown in these graphs. And they use this information to calculate out average temperature of the Earth. So here we can see the temperatures using the data. They put the data into a model to get a better sort of approximation. Okay, and here is another graph showing some of the stuff that they did, some of the data. The level of cooling is equivalent that occurred during this last glacial maximum to an equilibrium climate sensitivity of 3.4 degrees. So somewhere in between 2.4 and 4.5 would be our 66% probability range. And they define equilibrium climate sensitivity is the long-term temperature rise in global mean surface air temperature that will occur with a doubling of CO2. So we estimate that CO2 will reach 560 parts per million in about 2060. So this is a little bit lower than the estimate, the wide estimate of. Oh, sorry. This estimate here isn't 66%. It's more like 95%. And then here's RCP6 IPCC model. Consensus is about 3.7, so about 0.3 degrees warmer than what they came up with. And the range, I think it's a 95% range. It's not the 66. It is between 2 and 5 degrees Celsius. So as illustrated here. To come up with their estimates of equilibrium climate sensitivity, they took the data that they collected from these sea cores and then plugged it into a model. And in that model, there was 3 variables that were influencing global temperature: greenhouse gas forcing, so the effect of greenhouse gases, changes in albedo associated with expanded land ice, increased reflectivity from larger ice coverage in the northern hemisphere, and lower sea level, and then increases in the amount of mineral dust in the atmosphere. In the final graph from the paper, the thing to focus in on is what's in this red box. So there is their average value And in here they have all the different components. So we've got the effect of ice, the effect of aerosols, the effect of greenhouse gases, and it's variable in the model, and with an average of whatever I said, back up here, 3.7 degrees Celsius. And that's just the end of that paper. But it provides more evidence that our current sort of estimates of this equilibrium climate sensitivity are in the right ballpark. Okay, so let's now look at a chapter from that AR6, the first chapter that introduces this problem of human-caused climate change and global warming and change in precipitation and many other factors. So the chapter is called Chapter 1, Framing, Context, and Methods. So this is the 6th report, published in 2021. And it opens by suggesting that human activities have and continue to have an effect on the radiation balance and the climate of the Earth. And the main factors that are responsible for this modification of the radiation balance, and therefore these warmer temperatures, is greenhouse gas emissions, changes in the loading of aerosols in the atmosphere, which in general have a negative effect. They dampen the effect of greenhouse gas emissions, and land use change. So removing darker colored forest and turning it into cropland, which has a higher albedo. So these changes are modifying the planet's weather and climate, and this AR6 report is all about documenting what we know about this. Now, at first, it was very hard to identify that climate change was taking place up until about the mid 1980s, because it was hidden by the natural variability that occurred in something like global mean temperature, the variation that occurs from year to year due to factors like El Nino, La Nina, the Pacific Decadal Oscillation, and several other types of oscillations that exist in the climate system. However, as time passed and we gathered more data, the signal became more clear that we were modifying the climate, and this modification was much greater than natural variability. We now have an obvious signal in terms of global average temperature, and we have data that goes back over 100 years. So, for example, we can reconstruct global mean temperature, and the next graph shows this reconstruction from 1850 to 2020. And from this, we can see two periods of increasing temperatures due to greenhouse gas forcing on the climate system. There seems to be an increase that started at the beginning of the 20th century, ending around 1940, and then about a 30 to 40 year hiatus that was caused by our loading of the atmosphere with aerosol that reduced the amount of incoming shortwave radiation. And then starting in about 1970-75, the most recent trend in rising temperatures. And it's much greater than the first phase. So let's call it the second phase of rising temperatures. And on this graph, the data ends at 2020, where we can see the average temperature of the Earth is 1.26 degrees warmer than the baseline of 1850 to 1900. And by the end of 1940, it looked like temperatures were about 4 degrees warmer, and then it fell back down during that hiatus period to about 2 to 3 degrees Celsius, and then taking off and gaining about a full degree of warming of the whole planet between 1970 to 2020. And we know that the value of for 2023 is just below 1.5. I can't remember the exact value. Here's some reconstructions of past concentrations of carbon dioxide in the atmosphere. So we can see that it never really, over the last 800,000 years, it never went over 300 parts per million, and we're currently at about 425 parts per million. So here's the data since 1850, ending in this average period, and we're at about 400 parts per million at about 2015 to 2018, and another 25 parts per million for up to 2023. And then here are the estimates of how much carbon dioxide will be in the atmosphere under the different emission scenarios. So here is for the end of the 21st century. So approximately, and this is equivalent. So we're talking about could be as high as over 1,500 parts per million. So this includes methane and nitrous oxide. Here's SSP2 7.0 is about 900. Here's that best case scenario that we hope to hit, which would be equivalent to about 600 parts per million. And then here's further on into the future, at the end of the 23rd century, what the levels will be. Here is global surface temperature going back to 800,000 years ago, and it's a relative temperature, so relative to 1850 to 1900. So we can see that it got to about 1 degree above that value. So what we have today at about 400 million years ago, about half a degree, looks like about 350, and then it hit just under 2 in this last period here of glacial retreat. And then here we see the current trend up to 2014, and then what's estimated to occur in the future. So there's the worst case scenario, 4 degrees. Best case scenario, about 2.5 degrees. And then further into the future. Now, these last two emission scenarios, when they hit 2100, they're still increasing, and they will increase into the future before they level off. The others, 4.5, 2.6, and a new one, 1.6, level off before 2100. Predicting future rates of climate change is still very uncertain. We don't understand exactly how the atmosphere is going to work under the higher greenhouse gas concentrations, and we have a good understanding, but not an absolute one where we can predict things accurately. Most of the uncertainty is related to how we will generate energy in the future, which is kind of interesting. So it's not really how the climate system works. It's about what concentration of greenhouse gases will human development put into the atmosphere up to 2100. Will we, by 2100, will we continue to consume mainly fossil fuels? Or are we going to, quickly, within the next 30 years, switch from fossil fuels to renewable energy sources? The next figure describes what are the main drivers to climate variations on our planet, and internal to the climate system. So they include natural fluctuations in solar output, the concentration of aerosols in the atmosphere, which influences the amount of clouds. More aerosols generally produce greater cloud cover, greater reflectivity, concentrations of ozone, and that's in the stratosphere, and that ozone it acts as a greenhouse blanket to reduce losses of long-wave radiation and send it back down to Earth to reheat the atmosphere system. Greenhouse gases and large aerosols, their effect, and then changes to surface albedo due to either vegetation changes or snow or ice cover, ocean changes in ocean color because of differences in waves, if wind increases or wind decreases. So these albedo changes are built into the model. We know that ice and snow are going to reduce their coverage in the future, and that's going to lead to a positive feedback mechanism where more solar radiation is absorbed at the Earth's surface. So the natural drivers of climate change include variations in solar output. Volcanic aerosol loading is quite important. The Milankovitch cycles, the cycles between the sun and the Earth, and orbital shape, tilt of the Earth relative to the sun, and then changes in biogeochemical cycling, which are more long-term. Anthropogenic drivers include emissions of greenhouse gases like carbon dioxide, methane, nitrous oxide, and haliocarbons, so CFCs, chlorinated fluorocarbons, changes in atmospheric aerosol loading, and then changes in land use change, which is changing the albedo of the surface of the Earth. So in terms of aerosol loading, we know that with the advent of industrialization and after World War II, we started dumping a lot of aerosols into the atmosphere, and it had an effect of dampening the climate change that should have taken place, the global warming that should have taken place from about 1940 to 1970-75. And it's interesting that this aerosol loading is one sort of suggested thing that we do to the atmosphere. We do this on purpose in order to reduce climate change. It's important to remember that the Earth's climate system is mainly driven by solar shortwave radiation. However, over the last 100 years, we haven't seen much variation in solar output. There may have been during the Little Ice Age, but there definitely hasn't been any large change in solar radiation in the last 100 years. Now, the Earth's radiation balance is based on shortwave coming in, long wave leaving, and the dynamics of this flow are not simply input equals output. Additional heat energy is being added by the greenhouse effect. And this additional heat energy globally is about 33 degrees of Celsius. And 1 degree of that is, a little bit more than 1 degree, is what we've added. So adding more greenhouse gases to the atmosphere, we cause the release of more heat energy at the Earth's surface and within the atmosphere, and the amount of heat energy released to date is between 1 and 1.2 degrees Celsius. And, current estimates suggest because of El Nino, it's just under 1.5. Figure 1.2, which follows, shows all the feedback mechanisms working in the climate system when CO2 and temperature increase. So when we increase CO2, it causes an increase in global temperatures, and it leads to a whole bunch of feedback processes. For example, increasing CO2 and temperature changes cloud dynamics in the Earth. That has both a positive effect and a negative effect. The positive effect is related to high cirrus clouds, which do a greenhouse effect. And then the negative feedback is low-level clouds, like cumulus clouds, which have a negative effect of reflecting shortwave radiation back to space. Clouds at low and middle altitudes, as I said, act to reflect solar radiation back to space. More of these clouds means less energy input. So there's maybe something else we can do to engineer our way, in a way, to reduce the amount of global warming that takes place. So here's these feedback processes. Water vapor is going to increase. Clouds, some will increase, some will decrease. Lapse rate in the atmosphere will decrease. So it'll get less steep. The amount of long wave radiation will decrease in the atmosphere, leaving the Earth. Snow and ice, albedo, there will be a positive effect on the Earth's climate. Ocean circulation could have a positive or negative effect. Change in peat and permafrost is going to have a positive effect, releasing more carbon dioxide, methane, and so on. So these are some of these feedback processes that are now well known by scientists. Remember I talked about the high altitude clouds. So these are cirrus clouds, and the cirrus clouds influence outgoing long wave radiation. They send some of it back to the Earth's surface, where it creates more heat energy, and that heat energy goes into the Earth's surface and into the atmosphere. Atmospheric water, as we increase the humidity of the specific humidity or absolute humidity of the atmosphere, it's going to cause a positive effect, causing more greenhouse effect. And there's more and more, there's other effects in here. What's quite obvious from figure 1.2 is that the Earth's climate system is complex. And as I said, we do have a pretty good understanding of how the climate system works. But is it good enough to accurately predict what's going to occur in the future? Well, obviously not, if the models that we build with slight modifications give us a range of temperatures from 2.6 to 3.9 degrees Celsius of global warming with a doubling of CO2. The next figure, figure 1.4, shows some of the changes now occurring on our planet since 1850. And so we're talking about changes that are taking place in the atmosphere, the biosphere, the cryosphere, and the ocean. And the cryosphere is not about tears. It's about all the snow and ice on our planet. So that's comic relief. So here's CO2 concentration in the atmosphere, and it's been increasing, right? We've gone from about 280 parts per million to over 420. Precipitation, in terms of millimeters per year, it's changing depending upon the location. Some areas are getting wetter, some areas are getting drier. Glacier mass balance, we've seen steady decreases in glacial mass balance starting around in about 1960, and they've been accelerating. Global temperature, so we've gone from cool to warming. That stopped in about 1945, 43. Then a slight cooling, warming, cooling, and then it took off again in the 1970s. Global sea level has been increasing since about just early in the 20th century, and the sea level rise is increasing in its rate, and so we're now in the ballpark of about 20 centimeters rise in the last since the beginning of the 20th century. And then here, this graph shows ocean heat content, and it's been rapidly rising since about 1960. Computer modeling of the future of the Earth's climate it has started about 32 years ago with the IPCC, and it's developed rapidly. We've gone from very simple one-dimensional models to very complex Earth system models and 3D circulation models. The sixth assessment report employed over 100 different models from simulations in 100 different models from 49 different modeling groups to predict the potential future climate outcomes by 2100. In the history of the IPCC, we've gone from predicting global temperatures to predicting temperatures, changes in temperature, precipitation, wind, a whole bunch of variables at the local scale. So from very, very coarse global predictions of mean surface temperature to fine detailed predictions about a variety of climate variables at the local scale. So the next slide, also called figure 1.4, shows summaries of near future predictions from the first 4 IPCC reports. So this actually comes from a previous AR5, an old version. So these were the ranges of temperature change that they predicted to occur up until about the end of looks like about 2040. So this is the first assessment report. There's the range. Second assessment report, third assessment report, and the fourth, and the different emission scenarios. We'll examine the most recent predictions using these additional models in this sixth assessment report. Now, the purpose of modeling is not to predict the most likely outcome. It's to predict a range of outcomes. What's interesting is the range of outcomes. There really isn't anything that we can say is nothing to worry about. If 2.6 is the lowest predicted change in temperature by doubling CO2, that's still much higher than the 1.5 threshold that scientists say that we shouldn't cross. And of course, 3.9 will cause, we're dealing with climate change that's 3 times greater almost than 1.5. The main factor controlling the range is future rate of greenhouse emissions and how quickly will we replace fossil fuels with renewable energy sources. So in terms of the different emission scenarios that we have for the future. Here in this graph, we see predictions on where CO2 concentration will go into the future. So we're dealing with up to 2035. So you can see the range, and of course, this is when the first assessment report was released, 1990. There's the second report, third, fourth, and their estimates. here is predictions of where methane is going to go into the future up to 2035, and then finally nitrous oxide. What's really important to recognize in the last two assessment reports is that research has detected an uptick in extreme precipitation and warm temperature events. And in BC, we saw evidence of this in 2021 when we had the extreme temperatures that occurred in most of BC in late June 2021. And then in November, we had an extreme precipitation event that caused flooding from Vancouver Island, in fact, all the way into Merritt. There was high levels of precipitation that led to disasters and then landslides and so on. Now, this uptick in extreme events was predicted by theory and climate modeling. And some of these were very easy to predict because like temperature extremes follow a normal distribution, and all you're talking about is a shift in this normal distribution. The prediction of these future precipitation extreme events was a little bit more difficult because there the distribution is usually skewed, but it still can be done. It's a little bit more difficult. So here we see what should happen in terms of increase in temperature. We should have fewer cold extremes, more hot extremes. In terms of precipitation, we should be getting more heavy precipitation events and fewer small precipitation events. Let's stop there, and we'll continue this next week on Monday.